Hello everybody, this is a CPD presentation on the challenges of fire detection in data centres. It's particularly focusing on some of the aspects with regard to trying to detect relatively small volumes of smoke which are created by electrical overload in an area where high airflow is going to move that smoke very quickly. So if we move on, the agenda for it is to look at what the fire risk is. I think that's probably a fairly easy one to cover, but we'll talk about what the problems are. We'll talk about the issues of standard detection. So when we talk about standard detection, we're talking about normal optical smoke detectors that you'd find on the ceiling in an office type building. We'll look at the airflow considerations and some of the impacts that can have on detecting, and we'll also then talk about how sensitive a system should be, and then that moves us on to what an aspirating smoke detection system is, and aspirating is synonymous with being high sensitivity. We'll look at some of the design considerations. This isn't a design session by any stretch, but it's to just give you an idea of what the sort of design philosophy should be. And we'll also talk about how a design would be validated. And then there's a little bit at the very end about covering our product lines. So the objectives of this is to understand the impact of high airflow on smoke and what detrimental effect that's going to have on smoke detection performance, to have an awareness of the benefits of aspirating detection in data centers, and to gain an appreciation of the benefits of a performance-based design approach, where we look at how do we improve things beyond just basic code. So what is the fire risk in a data center? It is a pretty straightforward thing to consider. It's obviously mostly the electrical sources. Data centers by their very nature are very heavily loaded with power demands, and because of all of that electronic equipment within a data center, there is a very high risk of an electrical related fire. So the computing equipment that is in the data center is obviously the biggest chunk of that, but also UPS systems and battery storage systems that form part of the backup process of a data center application, and also things like air handling systems. So the air handling to keep the equipment cool is one of the biggest things that affect fire detection, but also it's also quite a high fire risk object in its own right. So fire risk can be through small works. So hot works permits would obviously be needed, and if somebody's going in to do some work and there's any careless activity, there is a potential fire risk there. The lighting within the data center is obviously quite a big fire risk. Even if a data center is deemed to be a black data center, no lighting on, there will be lighting within the facility. Therefore, there will be electrical systems serving those bits of equipment. And detection is needed as soon as possible to mitigate downtime. One of the biggest risks to a data center is them not being able to operate and the consequential loss of them not operating. So not necessarily the physical equipment within the data center. Of course, an operator doesn't want to lose a data center at all, but even a small fire could stop operation of the data center itself, and replacing the equipment may not be a big problem, but the consequential loss of the data center operating is a big problem. And then there's future equipment failure, which can be created by PCB corrosion as a result of smoke contamination. So the particulate given off from even a relatively small fire, that particulate can coat printed circuit boards, and then the coating on the printed circuit board, when it comes in contact with humidity within the data center, can lead to later corrosion of that printed circuit board, which will potentially increase the demand to replace servers within the facility. So trying to detect a fire as quickly as possible is a critical aspect of data center operation. So what are the issues of conventional detection? If we look purely at fire codes, and when we're designing systems, fire codes are all geared around smoke rising from a fire and hitting the ceiling and spreading it across the ceiling. So the position of conventional smoke detectors is typically on ceilings or in voids over those space and at the top, at the highest point of those areas. Conventional detection performance is compromised by high airflow. So if the normal rise of smoke because of the heat behind the fire doesn't happen because the airflow is too great, that smoke isn't necessarily going to get to where conventional detection would be placed. But also conventional detection is generally only a class C level of sensitivity. We'll talk about sensitivity classes in a bit, but essentially Class C sensitivity is the normal level of smoke detection performance that you'd expect in a data hall type, in an office type environment. But also access to detectors can be an issue, particularly if the picture we're looking at here is clearly a data hall of some description. There is a raised floor and there is a false ceiling. So fire detection will need to be in the facility, but it also, because of codes and standards, may need to be in the void space above the data hall if that void is deep enough, and also in the void space below the data hall, also if that void is deep enough and warrants the detection. So putting conventional detectors into these void spaces, there is a maintenance aspect associated with gaining access to maintain that system. And also smoke, particularly in the very early stages of an electrical fire, is diluted by the large spaces and the high airflow. So we're trying to detect in a data center a fire happening at the very early stages, and is there a risk of that fire affecting performance? Is the smoke coming off that fire being too low density of smoke and we're not detecting that fire condition? So airflow is one of the biggest factors that affect fire detection. If smoke is pushed away from the point detection's placed, it's never going to go off. So we need to try and consider the airflow environment within that space. This is a fairly typical example of a computer room. It's a little bit misleading because it does show a cold aisle, so a containment aisle, but actually there's no containment beyond that. But that's possible. That can happen. So the cold aisle is then pushing the airflow through the equipment. The equipment is where the fire is potentially most likely to occur, and that smoke is then going to follow back with the airflow back to the air handling unit, which is drawing air in typically at the top, has got filtration, so that filtration is going to remove any smoke particulate from the system, and then it's going to blow back into the floor void. So airflow is one of the biggest factors. The triangles indicate where potentially a conventional fire detection system would be fitted. So the AHUs will move the smoke with no thermal energy from an incipient fire away from those smoke detectors. So the smoke won't pool on the ceiling and spread as it would normally do, and therefore there's reducing the chance of a smoke detector actually picking that fire condition up. But also, as I said, the filtration in the air handling unit. If the air handling equipment is very good, the filtration is very efficient. If any low levels of smoke are drawn back to the air handling unit, they won't come back out, and we've effectively lost any chance of detecting that smoke once it's got back to the air handling unit. So containment aisles, the previous picture was showing a cold containment aisle. This picture is showing a hot containment aisle, which actually we could argue is going to create even more of a problem, because then the fire detection in the main body space of the data hall, smoke is very, very unlikely to get anywhere near these smoke detectors positioned on the ceiling to code. So in this case, we've got a cold aisle feeding air into the hot containment aisle through the chimney and back to the return air grill over here. So in all cases, when there's an air handling system, the air handling unit will draw airflow back to it, but the intake grill may be remotely positioned based upon what airflow is happening prior to that air handling unit. So in this case, this example is showing a closed system. So we're recirculating the air through the air handling unit, past the filtration, past the cooling, and back into the floor void. But actually, to compound the problem yet further, if free cooling is deployed, where we're drawing air in from outside because it's more efficient to use colder external air than it is using cooling the air inside the space, then any smoke is immediately going to be taken out of the facility and even more lost than if it was going through the air handling process. So this is critical from a design perspective when people are looking at air handling systems within or fire detection within data centers, is fully understanding what the airflow characteristics are, what's occurring with that airflow. So just further talking about containment aisles add complication. We've talked about that already. However, AHU return air grills still exist. We've talked about that already. And again, this example here is showing a hot containment aisle, and then we've still got air handling units, and we've got a return air grill at this point, which is critical to fire detection. Compartmentation should also be considered with containment aisles. Actually, containment aisles are a good thing from fire detection point of view, because in the past, when a data hall was just one big open space, it was very hard to find the very first stages of a fire condition, even if detection had occurred, because you've got to try and track that fire down. Whereas actually with a containment aisle, we can now pinpoint, if we got careful design, we can pinpoint to a containment aisle. BS 6266 is the British standard for fire detection systems in electrical data processing areas and areas of high airflow. So it's the standard that should be followed for fire design in particularly the UK, but it is adopted in other parts of Europe as well. But it's the standard that should be followed with fire detection design in these types of applications. And one of the things that this talks about is hot and cold aisle containment, and it's effectively saying that cold aisles should be an extension of floor voids or ceiling plenums. So it's just describing what should happen in an environment where there might be fire detection in the subfloor area, but that fire detection also needs to be in the cold aisle as well. And in this case, the cold aisle is the main body, the main area that the data center is accessed from. So what sensitivity should be deployed? We mentioned earlier, conventional detectors offer only a Class C normal level of sensitivity, so the same as you'd have just in a normal office environment. And is that adequate for a computer room? Most computer rooms do demand earlier detection, so a data center operator is going to want to have a fire alarm as early as possible, within reason, so that they can react to the problem quickly, so that they solve the problem of downtime. So standard optical detectors can't give that level of coverage. Within BS 6266, there is a risk assessment section which takes the reader through some of the criteria that they have to consider when they're risk assessing a space. And within that, areas fall into either a high or a critical risk category. So within the high category risk, we've got things like IT facilities, telecoms facilities, and production control computers. And in critical categories, we've got financial dealing, data centers, computer operations, internet hosting, air traffic control, and nuclear chemical facilities. So you can see within those that when we're talking data centers, typically they would fall into what would be deemed to be the critical category risk of a risk assessment. When we then look further, there's quite a few words here, but the snippets come from BS 6266. When we look further, when we look at medium, high, and critical risk categories, when we look at high and critical data centers, it talks about we should be looking at a Class A high sensitivity aspirating smoke detection system to monitor the return air conditioning. So already the standard is saying that you've got to have high sensitivity across these return air grills, because it's clearly understood that that's where smoke is going to go. I won't go through all the words in this bit here, but this is also talking about the benefits of having Class A detection within the main body of the building, so comprising the sole means of fire detection in the monitored area. So not only across just the return air grills, but also potentially across the room space as well, and floor voids and ceiling voids within that area. EN 54 Part 20 is a product standard that affects aspirating systems. EN 54 relates to all fire detection equipment, and then the part relates to the particular product type. So Part 20 is aspirating. So it's up to the manufacturer, us, to get our products approved to EN 54 Part 20. And what EN 54 Part 20 it does is it introduces sensitivity classes. There's lots of other testing, but if we're focusing purely on fire detection, it talks about sensitivity class. And whenever an aspirating system is being designed, the capability of that aspirating system has to be considered. And the capability is the maximum number of sampling holes that can be applied to one unit to achieve the sensitivity class. So if you want normal level of sensitivity, you can typically have a lot more sampling holes than if you want a higher level of sensitivity where there's a greater demand on the system and therefore less sampling holes on the system. It also talks about maximum transport times. One of the things that affects aspirating systems is how long does it take for the smoke to travel through the pipe back to the detector to be analysed for smoke. And of course, that's then comes down to the transport time of the system. And when we test our products in the fire test room at the regulatory body, effectively each sensitivity class has a lower level of smoke density within that fire test room to give the same level of alarm condition. So when we look at the sensitivity classes, what we're interested in this topic of conversation today is a Class A system. So high sensitivity Class A computer rooms, data centers, that type of application. When we look at enhanced sensitivity, Class B systems, that's where we've got a risk of large volumes of dilution. So in atrium, shopping centres, warehousing, that type of environment. So not really relevant to this conversation today. And then when we look at normal sensitivity, this again, just as a reminder, this brings it back to being comparable to point detectors. And with an aspirating system, we're talking individual holes. So one sampling hole being subjected to smoke has got the same performance characteristics as a conventional smoke detector. So this is Class C, and that's in normal areas. So normal applications, ceiling voids, floor voids, for example. So in a data hall, it might be that the ceiling void above the data hall needs fire detection, but it isn't being used as part of the airflow within that application. So it's not a return air plenum. So it's a still air environment. It can have normal Class C levels of sensitivity in that void space above the data hall. If the ceiling is being used for return airflow, then it needs to be a Class A level of performance within that space as well. So we've talked about aspirating, so you may not actually understand what an aspirating system is. So just very basically, it's a system which is actively drawing air from an area via a pipe network with sampling holes or capillaries in the pipework to a central detector which monitors for very small amounts of smoke. So this is the detector. This is the VESDA unit. It is a detection device, so it falls under the criteria of smoke detector. It's not a control panel or a control system. And then connected to this is the pipework. And that pipework will either have, as this picture shows, capillaries, and all a capillary is a small flexible tube coming off of the main pipe, which is 25mm plastic typically. So we can sample from a different location. So in this example here, the pipe is in the void, but we're sampling from the room space below in the data hall below. But if that pipe was the pipe protecting the ceiling void, then we typically just have holes in the pipe. So that air is being drawn back to the detector where it's being analysed for smoke, and then the unit will trigger and volt-free contacts will trigger the fire alarm system to interface to the cause and effect requirements of the application. How sensitive is VESDA? If you look at a conventional smoke detector, most smoke detectors, and they do vary depending on the manufacturer, but typically between 4 and 6% obscuration per meter. So all smoke detectors they're sensitive, their performance is measured in obscuration per meter. So if you had a meter path of a light source and the receiver saw a reduction in that light path, that is obscuration per meter. So most smoke detectors are doing between 4 and 6% obscuration. With VESDA, our first level of alarm, and we've got multiple levels of alarm, and they're just completely independent and they can do whatever the cause and effect requirements of the site are. But we can have an alarm from 0.005% obscuration per meter right the way through to 20% obscuration per meter. So we've got a very broad range of sensitivity, which is why this unit can be applied to either Class A, B, or C applications to give the sensitivity criteria needed for the job. So when we look at aspirating design, there's various things we have to take into consideration. So primary and secondary detection is critical. We'll have a quick look at the standard and sighting of conventional detectors and how we relate that to the pipe network. So secondary detection is normal smoke detection positioning. Now, in a data hall, secondary detection could be normal optical smoke detectors, or it could be an aspirating system, just depends on the design or the customer's requirements on this particular application. So our secondary coverage is in its normal ceiling level or top of void detection. So these are secondary smoke detectors. And if we had floor void detection as well, this would be at the top of the void. That's also secondary detection. But if we look at this picture again, we can see that obviously the smoke detectors in the cold aisles are never going to see smoke because the smoke is originating from the equipment in the servers. Even the smoke detectors at the top of the void, if this void is quite deep, let's say it's a couple of meters deep, if the airflow returning to the return air grills is very laminar, that smoke may never get to the top. So even with aspirating detection up here, there is a risk that it would never detect a fire condition if we relied purely on our secondary protection, which is why it's critical to think about primary protection. So protecting in the return air path, positioning the pipework from an aspirating system where we know smoke will end up, even in very low quantities of smoke, because we can detect very early at very low levels of smoke density. Positioning where we know that smoke is going to get drawn to is going to aid detection. So in this case here, although this is the top of the air handling unit, we don't want to protect at this point because we could be looking at a fresh air system, as this is showing, drawing fresh air in from outside for free cooling, and that smoke is going to leave the building. So this is our primary detection point here. But I mentioned earlier, actually, containment aisles are beneficial to fire detection because we can then start to address more directly where that smoke's coming from. If we were to detect only here, we'd only know that it's within the equipment being fed from these two containment aisles. Whereas if we also detect at the top of the extraction hood of the containment aisle, we can then pinpoint to say it's in this location here. And that's perhaps particularly important for not only trying to identify where the fire's starting, but also for the risk associated with people working in this facility. It's very important, particularly with containment aisles, that there's adequate fire detection within the containment aisle and also adequate alarm signaling in the containment aisle, so that if somebody's either working in there or is about to enter that cold aisle, that containment aisle, they know that there's a potential problem within that space. So from a design perspective, this is just a very, very general coverage. Within BS 6266, it talks about a conventional smoke detector having an area of coverage of 25 square meters. Now, if anyone understands fire design for normal applications, we designed to BS 5839, and a conventional smoke detector can cover 100 square meters. So in a computer room type environment, we need 4 times the number of either optical smoke detectors or sampling points from an aspirating system. And again, it's important to point out that this is just for top of void detection. This is not primary detection. So here's an example, very, very basic computer room. It could be this simple. It may not be a very advanced design system, so it may not have containment aisles. But in this case here, we've got an aspirating system covering the room space, and each of the sampling holes taking the place of an optical smoke detector is covering 25 square meters. But of course, within the design, we've got to consider the return air grills as a priority. If aspirating is only ever used at one point in a computer room, it's across the return air grills. Conventional detectors can be used elsewhere, but obviously there is a benefit to having high sensitivity within the facility as well, because if the air handling units fail for some reason, firstly, there is a greater chance of a fire alarm condition occurring because there's a greater risk of fire starting because there's no cooling, and we've still got high sensitivity detection protecting the space as well. And it's also important to point out here from a design perspective, when we're looking at design of aspirating, you've got to consider the capability of the system. So is the detector capable of having this number of sampling holes connected to it and still achieving the sensitivity requirements for a Class A application? So that's down to the design of the system and the product chosen to be used. So return air detection is critically important for early detection. So positioning the VESDA detection at the return air grills ensures the greatest chance of detecting diluted smoke in the airstream. All grills that impact further smoke detection should be considered. So if the grill takes smoke from the facility and removes it completely, it does need to be covered. So for example, the computer room return air grill, because it's going to go through filtration, or pressure relief vents. Now, these aren't pressure relief vents to do with gas extinguishing. If you have a gas extinguishing system in the data hall, there will be an overpressure vent to stop any damage within the facility. The pressure relief vents we're talking about here are the ones that happen when free cooling starts. So in this example here, I'm not sure exactly of how this is. This is the return air grill, but at the moment it's closed down because there's a free cooling process in place, and this is the pressure relief vent, and both of them have got fire detection. So there's the VESDA pipe across it, and there's the VESDA pipe on the pressure relief vent. Similarly, this one here, much more basic. This is a British Telecom facility, and when the free cooling is in place, it just creates an overpressure in the room, and these are just weighted flaps, and the weighted flaps open up to allow that pressure out. But again, it's important that the detection is here, because if there is low concentrations of smoke, it's going to leave the facility through those pressure relief vents. The FIA Code of Practice, we haven't talked about this yet, but the FIA Code of Practice is a guidance document which talks about aspirating detection systems. And also the FIA have written a document recently with regard to detecting smoke in high airflow environments. So two very, very good documents which give guidance. The FIA Code of Practice gives guidance on the maximum number of sampling holes being 0.4 square meter maximum with no less than 3 holes across that grill. So there is design guidance in there, and also BS 6266 takes a very similar stance on how you protect those return air grills. So it does give guidance on the number of holes needed to protect those return air grills and pressure relief vents. Performance-based design is something that as a manufacturer we've talked about for years, and it's basically just saying what can you do beyond the code to make the system more effective? Is there any way that you can improve detection performance? So taking this as an example, as we rely on detection at return air grills, it is important to know the airflow path, so performance-based design. The picture below shows an air handling system where the return air path is actually at low level. It's quite an unusual one, but not completely uncommon in data halls. And what we've got here, it's not a very clear picture, but here are the server cabinets down here. And actually the air handling units are drawing air in through the bottom here, cooling, and then taking them up through ducts to then be blown down through the cold aisle to leave the hot aisle, and the hot aisle is basically just the data hall. So this is actually pushing air downwards as opposed to the fairly typical approach where air is going upwards. And this would have a major impact on smoke detection because the smoke is immediately being taken away from the normal position that smoke detectors would be located. So it's very important to understand the airflow characteristics within a data hall to make sure that the primary protection is being deployed correctly and the best possible solution. It's also very important that the system performance is validated. So as we said before, all ASD systems have a maximum capability. So how much pipe, how long can the pipes be, and how many sampling holes can be connected to still achieve the requirements of a Class A sensitivity system. So design should be validated with a computer model that shows its capability is not being exceeded. Added to this, the limitations of area of coverage of sampling holes and detection systems as detailed in British standards. So the British standards have to be followed, and the computer model that validates the design just says, yes, it will work within the capability of the detector and achieve the sensitivity criteria needed for the system. But also transport time is critical here. We don't want transport time to be too long, because if the length of time it takes for the airflow to get back to the detector is so long, it's going to delay the response time that we need for that system. So we have to look at transport time. The pictures here are an example of the model that we have. So Aspire is the model to validate VESDA detectors, and it's not clear, but this is saying that we need to have a Class A level of sensitivity, and it's actually telling me that I am achieving Class A sensitivity. And this is the three-dimensional model, and we can see from this is probably one detector serving 3 air handling unit return air grills up here. So we know we're achieving the sensitivity criteria, we know we're achieving transport time, even before the system starts to be installed. So it is important to request when you're designing or getting involved in data centers, that it is important to request a design done prior to installation of that system. It's also important to look at the validation of the system performance on site. So when a system's complete, performance testing should be conducted. It's not critical. If a system is installed exactly to standards, then you don't have to do a performance-based test, but it's always well worth doing. And it's one thing that's very different about aspirating to a conventional detector. When a conventional detector is tested, all that happens is the service engineer puts a smoke cup over it and injects an aerosol smoke into it to prove the system works. It proves the detector works. It proves the signal to the fire panel works. It doesn't prove that a fire within the facility would be detected. And that's what performance-based testing is. And the most common one used in computer rooms is the 1 meter or 2 meter wire burn test. This is a picture of it. It's basically just a piece of wire typical to British Telecom. Actually, they were the ones that sort of developed this back in the 80s, this test. And it's an overloading of that wire to create smoke. And you can see here, this is an extract from BS 6266, and it talks about the type of test that should be done depending on a class A, B or C application and what the design is. So primary, secondary, for example. So it tells you what type of fire test is done. And it's always worth doing it. And again, it's important to point out that what this doesn't prove is it doesn't prove individual sampling holes detect. It proves the system within the facility will go off. And it might be that there's 6 Vestas in the space, and if two Wyburn tests are done, only 2 of the detectors actually detect, the others don't. It doesn't say the system's not working. It proves the design performance is being met. So ASD product selection, what type of VESDA or what type of aspirating unit should be used? It does depend on primarily the detector's capability. So does the detector being applied to the design achieve the maximum number of sampling holes required for EN54 sensitivity? What are the maximum pipe run lengths? What is the area of coverage to BS? So are we achieving from the detector that's being chosen the criteria for sensitivity within that application? We've also got to think about integration to other services. Most aspirating systems will interface to the fire alarm system via volt-free contacts. And again, it's important to point out an aspirating detector is only a smoke detector. It's a very clever unit, and there's a lot of functionality through the front that you don't get with a normal smoke detector, but it still needs to interface to the fire alarm control panel, particularly if that alarm control panel is doing building evacuation alarms. It might interface to the building management system, or it might connect via Ethernet or Wi-Fi. So there's a number of ways we're connecting to other things. It's also down to specification. Has the consultant specified a particular product? Has the customer got a personal choice? So the customer may choose that all of his aspirating detectors are going to be a particular manufacturer and also perhaps a particular type of unit, because most manufacturers have got a number of different detectors giving different capabilities. So this is a very quick overview of our product range. I'm not going to go through it in great detail. You can come to our virtual booth and we've got documentation on all of the equipment. So really it's down to what's the application, how big it is, and what sort of performance we're looking for. So we've got mostly 4-pipe systems. This is a single pipe system. The VEA is a microbore system, so 40 microbore holes. There should be a class A there. It is a class A sensitive unit. So this could be a good for protecting inside equipment cabinets. That's generally the only place it's used in a data hall. And then the VES is a 4-pipe system with addressability per pipe. So it's really down to how much pipe, how many sampling holes would dictate which one of the VESDAs I would choose to use for this application. Just a quick case study, just to give you an idea. So this is a document which I think is uploaded to our virtual booth. It should be there. It's SunGuard. There's 20 UK sites. Just to give you a feel for this. So 8 data rooms, 2 floors, 42 VESDA detectors. And the VESDAs are located across the return air grills and within the main data facility. So it's really down to the specification as to whether it would protect the room and the return air grills or just the return air grills. Also on this one, we're using VESDAnet. VESDAnet is the way we can join all VESDAs together. It's separate to the fire alarm loop. So the VESDA still interfaces to the fire alarm through the fire alarm loop, but VESDAnet allows then the benefits of using VSM-PC graphics. So having a central monitoring of the VESDAs within that space. It also allows us to do referencing. Referencing is very important. If we're drawing air from outside a space to inside, if there's a risk of smoke being drawn from outside into the facility, we could get an unwanted alarm. So in that case, we would use referencing to monitor that fresh air coming in to offset against any other potential problems within the space. And the VESDA provides early warning and operation with conventional detectors for pre-action of sprinklers. So they've got conventional detectors and aspirating. Triggers from both will do a pre-action of the sprinkler system, which is obviously the final protection of the data facility. And actually, the last point here, we're talking about the monitoring that fresh air being drawn into the space. Okay, that's the end of the presentation. Thank you for attending. If you want to come and talk to us, then please come and visit us at our virtual booth, and we'll be really pleased to talk to you there. There's a lot of documentation. There's design guides for data centers. There's various other documents to give you guidance on aspirating detection in data centers. You can also go to our website, which is shown on the screen just here, to gain more information and make contact with us. But if you've got questions, please, we would love to hear from you.